Now we want to adjust the cutoff level S to guarantee that our test actually has asymptotic level alpha. For this, we explored what we just showed about the test statistic Tn, namely its asymptotic normality. So we've just seen that Tn, which is the absolute value of square root px hat minus py hat, divided by square root 2p hat times 1 minus p hat, in distribution goes to standard normal under h0. That is, if both proportions are equal. And I might have forgot to mention it. Let's assume that both px and py are strictly between 0 and 1. Otherwise, we'll get into trouble with the division of 2p hat times 1 minus p hat here, this normalization. OK, so if we have this asymptotic normality, then we do what we've done a couple of times already. Namely, we just have to guarantee that when we cut off at level S, when we decide to reject the null hypothesis, that this, under the null hypothesis itself, has asymptotic probability alpha. So we want this quantity here to be alpha at the end of the day. But this is exactly the probability that the quantity I calculated for Tn exceeds level S. And by this asymptotic normality, by the convergence in distribution, as n goes to infinity, this goes to the probability that a standard normal random variable, let's call it z, exceeds level S. Right. And we want this to be alpha. And another way to write this is 2 times 1 minus phi of s, where this is the CDF of a standard normal random variable. And that means we will solve s to be the 1 minus alpha over 2 quantile of a standard normal random variable. Great. All right, so let's write this here. Q alpha over 2. OK, and now another thing we want to talk about is the type 2 error. So now we've seen that if h0 is actually, if the null hypothesis is actually true, then we will have asymptotically only type 1 error alpha. Exactly alpha. So what happens if the null hypothesis is not true? In other words, what happens if my proportions are actually different from each other? Will I actually be able to pick this up? Will I at least asymptotically not make an error? Right? And for this, let's just look at how we wrote down our test statistic. We have consistency of our estimators. That is, we know that px hat in probability goes to px, and py hat goes to py. Right? And also important, the variance that we're normalizing with, so the estimator we plug in there, p hat, is, I already wrote it down up there, that is the average of px hat plus py hat. That is also converging in probability. So this is as n goes to infinity. To the sum of the two, or the average of the two ground truth proportions px and py. So that means that Tn, if I write it out, looks like this. That means I have a quantity in the denominator that, under our assumptions that actually the probabilities are strictly between 0 and 1, then this whole quantity here in the denominator goes to some number. It goes to 2 times p. Let's call this p. Let's call it p tilde, see? 2 times p tilde times 1 minus p tilde. Right? So that's some number, some non-negative number. And these quantities here, so the numerator goes to px minus py, which is not 0 under h1. So this whole quantity, except for the square root of n, goes to some specific number in probability. And if I hit this with the square root of n, then that means that the whole term, the whole Tn, as n goes to infinity, actually in probability goes to plus infinity. That means as n grows larger and larger, if our model is true but the null hypothesis does not hold, then this quantity exceeds every fixed limit with overwhelming probability. In other words, actually pointwise, that is for fixed p of x, fixed p of y, and n going to infinity, we have vanishing type 2 error. That is pointwise. And also, if you want in probability, but you could strengthen those statements to hold almost surely, because all our estimators here actually, by the strong law of large numbers, also converge almost surely. Cool. So now it's up to you. I got to erase, and then we'll finish up with some remarks. How about you try to first derive the corresponding cutoff parameter for the one-sided test you were looking at, and then just plug in some numbers and see what happens. For example, at alpha equals to 10%.